Hello, friend. Welcome to Science for Sleep. Whether you are returning tonight or gently discovering this channel for the first time, this is a quiet place to slow down, learn something soft and interesting, and let the day slowly fade into the background. Tonight, we are going to explore the science of weight gain, not as a judgment, not as a warning, and not as a story about blame, but as a calm look at one of the body's oldest survival systems. The human body is always changing. It changes after a meal. It changes during sleep. It changes after a long walk, during a stressful week, through the seasons, across the years, and even across a single day. A number on a scale may look simple, but inside the body, that number can reflect water, stored carbohydrate, muscle, bone, digestion, blood volume, hormones, and fat tissue. It is not one thing. It is a whole body snapshot. And one of the most surprising parts of this story is that body fat is not just stored weight. It is living tissue. Scientists call it adipose tissue. Adipose simply means fatty tissue, but that name can make it sound still and quiet, like padding placed beneath the skin. In reality, adipose tissue is active. It receives blood. It responds to hormones. It releases chemical messages. It changes in size. And it speaks to other parts of the body in ways that scientists did not fully appreciate until fairly recently. For a long time, many people thought of body fat as a kind of storage closet. Extra energy went in, and later, if needed, energy came out. That part is true. Fat does store energy, but it is not the whole truth. Body fat is also part of the endocrine system. The endocrine system is the body's network of glands and tissues that send hormones into the blood. Hormones are chemical messengers. They travel quietly through the bloodstream and tell different organs what is happening. The thyroid sends messages that affect energy use. The pancreas sends insulin, which helps control blood sugar. The adrenal glands send stress hormones. And adipose tissue sends messages too. One of those messages is called leptin. Leptin helps tell the brain how much stored energy the body has. When fat cells grow, leptin levels often rise, sending information to the brain about the body's energy supply. Another important signal is adiponectin, a hormone made by fat cells that helps influence how the body handles sugar and fat. These tiny messages are invisible. You cannot see them moving through the blood, but they are part of the quiet conversation that helps shape hunger, fullness, energy use, and storage. If you enjoy these quiet journeys, you're welcome to subscribe. And if it feels natural, to leave a comment sharing where you're listening from tonight. It helps others find their way to this calm corner of the world, one sleepy traveler at a time. The quiet continues here, just as it is. So when we talk about weight gain, we are not just talking about size. We are talking about communication. The brain is listening. The stomach is stretching and emptying. The intestines are sensing nutrients. The liver is sorting fuel. The muscles are storing and using energy. The blood is carrying sugar, fats, amino acids, oxygen, and hormones. And beneath the skin, in soft layers across the body, adipose tissue is storing energy while also sending signals back into the system. This is why weight gain can never be reduced to one small idea. It is not only about one meal. It is not only about one habit. It is not only about movement. It is not only about willpower. It is biology. It is chemistry. It is timing. It is sleep. It is stress. It is the nervous system. It is the body trying, in its ancient way, to stay prepared. For most of human history, storing energy was protective. Food was not always available. Winters could be long. Harvests could fail. Hunting could take time. Illness could reduce appetite. Travel could require days of walking. A body that could save energy had an advantage. Stored energy could help a person survive when food became scarce. So the body learned to hold extra fuel carefully. It learned to store energy in a compact form. It learned to protect itself against emptiness. And even now, in a modern world filled with grocery stores, refrigerators, restaurants, desk work, artificial light, and late nights, that older system is still here, quietly doing what it was built to do, taking in signals, reading the body's needs, and deciding what should be used now and what should be saved for later. That is where the story of weight gain really begins. Not with appearance, not with judgment, but with a living body, full of moving signals, trying to understand the energy arriving inside it. Before the body can store anything, it has to translate food into a language the cells can use. A piece of bread, a spoonful of rice, a slice of apple, a bowl of soup, or a little olive oil does not enter the body as weight. It enters as texture, flavor, warmth, scent, and memory. Then, slowly and carefully, it becomes chemistry. Digestion begins before the food even reaches the stomach. When food is chewed, the teeth break it into smaller pieces, and saliva wets it so it can move smoothly down the throat. Saliva also contains an enzyme called amylase. An enzyme is a tiny biological tool that helps break larger molecules into smaller ones. Amylase begins working on starch, the kind of carbohydrate found in foods like potatoes, oats, pasta, and bread. It starts clipping long chains of starch into smaller sugar pieces. This is why a plain cracker can begin to taste slightly sweet if it rests in the mouth for a while. The chemistry has already begun. From there, food travels down the esophagus, a soft muscular tube about 10 inches long in an adult. It does not simply fall into the stomach. The esophagus squeezes in smooth waves, gently pushing the food downward. Inside the stomach, food meets acid strong enough to help unfold proteins and kill many microbes that arrive with a meal. The stomach also churns like a slow mixing bowl, turning food into a thick liquid called chyme. That word simply means partly digested food mixed with stomach juices. Proteins, found in foods like eggs, beans, fish, meat, yogurt, and lentils, begin breaking apart into smaller pieces. Later, those pieces become amino acids. Amino acids are the building blocks the body uses to repair muscle, build enzymes, support the immune system, and maintain skin, hair, organs, and blood. Fats take a different path. Fat does not mix easily with water, just as oil floats on the surface of soup. So the body uses bile, a fluid made by the liver and stored in the gallbladder, to break fat into tiny droplets. This gives digestive enzymes more surface to work on. A pat of butter, a handful of nuts, or the oil in a salad can then be broken down into fatty acids and glycerol. These smaller fat pieces can be absorbed and carried away. Most absorption happens in the small intestine. Despite its name, the small intestine is long, usually around 20 feet in an adult. Its inner surface is folded again and again, with tiny finger-like shapes called villi, reaching into the passing liquid. These villi make the surface area much larger, like a soft towel folded into many ridges instead of lying flat. Through this folded surface, glucose from carbohydrates, amino acids from protein, and fatty acids from fat begin crossing into the body. Glucose and amino acids mostly enter the blood and travel first toward the liver through a large blood vessel called the portal vein. The liver acts like a quiet sorting station. It can store some fuel, release some fuel, transform some molecules, and help keep the blood steady. Fats often take a slower route through the lymph system, a pale fluid network that helps move certain nutrients and immune cells. Eventually, many of these fat particles reach the blood too. By this point, the meal no longer looks like a meal. The apple is no longer an apple. The rice is no longer rice. The olive oil is no longer a golden liquid on a plate. It has become glucose, amino acids, fatty acids, minerals, water, and vitamins moving through warm vessels in the dark. The bloodstream carries these materials past the heart, through the liver, toward the muscles, into the brain, around the gut, and out to tissues near the skin. Cells wait along the way. Some cells need glucose quickly. Some need amino acids to repair tiny daily wear. Some can use fatty acids for energy. Some will save what is not needed right away. This is why weight gain begins long before the body looks different. It begins in the quiet work of turning food into usable material. A meal becomes molecules. Molecules enter the blood. The blood carries them through the body. And as those molecules arrive, the body begins sorting them with remarkable care. Some will be burned soon. Some will be rebuilt into living tissue. Some will be stored for later, held back like supplies placed gently on a shelf. And once food has become this moving stream of fuel, the body must decide what to use now and what to save. Once food has become molecules in the blood, the body does not rush to store all of it. First, it spends, quietly, constantly, even in complete rest, with the lights low and the body still. Energy is being used in thousands of small ways. The heart keeps beating. The lungs keep drawing air in and letting air out. The liver keeps sorting fuel. The kidneys keep filtering the blood. The brain keeps sending signals through nerves. Cells keep repairing tiny damage that happened during the day. The body is never truly doing nothing. A resting adult heart may beat around 100,000 times in a single day. Each beat uses energy. Each beat pushes blood through vessels that, if stretched end to end, would reach for many thousands of miles. The lungs may move roughly 20,000 breaths a day, depending on body size, activity, and health. Even when breathing feels effortless, the muscles around the ribs and diaphragm are still working. The diaphragm is the wide, dome-shaped muscle under the lungs. It lowers when you breathe in, making space for air to enter. It rises when you breathe out, helping air leave again. This movement is quiet, but it is not free. It requires fuel. The brain is even more surprising. It makes up only about 2% of adult body weight, but it uses around 20% of the body's resting energy. A soft grey organ, weighing about 3 pounds, is one of the most energy-demanding tissues in the body. It uses this energy to keep nerve cells ready to fire, to process sound, touch, memory, temperature, balance, emotion, hunger, and the steady awareness of the body itself. Even during sleep, the brain does not shut off. It changes its rhythm. It sorts information. It helps regulate hormones. It keeps watch over breathing, heart rate, and body temperature. So before the body stores extra fuel, it must feed this constant inner work. The liver is working too. It sits under the ribs on the right side of the body, weighing about 3 pounds in many adults. It helps manage glucose, stores vitamins, processes fats, breaks down old blood products, and handles many substances that enter the body. The kidneys, 2 bean-shaped organs near the back of the abdomen, filter the blood again and again. Each day, they can filter roughly 150 liters of fluid from the blood, while carefully returning most of that water and useful material back to circulation. Only a small amount leaves as urine. This is a quiet kind of precision. The body is not only burning energy, it is measuring, saving, cleaning, correcting, and balancing. Temperature also takes energy. Humans hold their inner temperature near 37 degrees Celsius, or about 98.6 degrees Fahrenheit, though it naturally varies a little from person to person and hour to hour. When the air is cold, the body may use more energy to produce heat. When the air is warm, it may sweat, sending water to the skin so heat can leave through evaporation. Even sitting still in a cool room, the body is making tiny adjustments. Blood vessels widen or narrow. Muscles may tense softly. Skin may release or hold heat. This steady control helps enzymes work properly. Enzymes, those tiny biological tools, depend on the right temperature to do their jobs. Movement is part of energy use, but it is not the only part. A walk across the kitchen uses energy. So does climbing stairs, carrying groceries, stretching, cleaning, standing, fidgeting, or turning over in bed. But a large share of daily energy is spent before any planned exercise begins. This is called resting energy use. It is the energy required to keep the body alive while at rest. For many people, it is the largest part of daily energy spending. It keeps the organs running. It keeps the blood warm. It keeps cells alive. It keeps the brain lit with quiet electrical activity. This is why the body treats incoming fuel with such care. Glucose from a meal may be sent to cells that need quick energy. Amino acids may be used to repair tissue. Fatty acids may be burned by some organs and muscles. The body is always matching supply with need. But after the brain, heart, liver, kidneys, lungs, muscles, and cells have taken what they need for the moment, the remaining energy does not simply disappear. Biology does not like waste. Fuel that is not needed right away has to be handled. Some of it can be held briefly. Some of it can be changed. Some of it can be saved. And the body has a short-term storage system ready for exactly that. When the body has more glucose than it needs right away, it does not have to turn all of it into fat. Some of it can be stored in a faster, shorter-term form. That storage form is called glycogen. Glycogen is made from glucose, the simple sugar that enters the blood after the body digests foods like rice, bread, oats, fruit, beans, potatoes, and pasta. A single glucose molecule is small, but glycogen is made when many glucose molecules are linked together in long branching chains. You can picture it like a tree made of sugar. A trunk, many branches, and smaller twigs, all packed tightly inside living tissue. This branching shape matters because when the body needs quick energy, enzymes can break glucose pieces off the ends of those branches very fast. Glycogen is stored mostly in two places: the liver and the muscles. The liver sits under the right side of the ribs, and one of its jobs is to help keep blood sugar steady between meals. When blood glucose rises after eating, the liver can take in some of that glucose and store it as glycogen. Later, when blood glucose starts to fall, the liver can break glycogen back down and release glucose into the blood. This is especially important during sleep. While the body rests for 7 or 8 hours, the brain still needs fuel. The heart still beats. The lungs still move. The liver helps bridge that quiet overnight gap, slowly releasing stored glucose so the body does not run empty before morning. The muscles store glycogen too, but they use it differently. Muscle glycogen is mostly saved for the muscle itself. A calf muscle can use its own glycogen during a walk. A thigh muscle can use it while climbing stairs. The muscles of the arms can use it while lifting, carrying, reaching, or pushing. This is why glycogen is not just stored energy. It is local energy. It is fuel kept close to where movement may happen. The amount stored can change from person to person. A larger body may store more. A more muscular body may store more. A person who has eaten more carbohydrate recently may store more. A person who has exercised hard may have less for a while, until the body fills some of it again. In many adults, the body may store several hundred grams of glycogen across the liver and muscles, though the exact amount depends on diet, activity, body size, and training. This storage is useful, but it comes with something many people do not expect. Glycogen brings water with it. For every gram of glycogen stored, the body stores several grams of water along with it. The exact amount can vary, but a common estimate is about 3 grams of water for each gram of glycogen. So when glycogen rises, water often rises too. This is one reason body weight can shift quickly. A person may eat more carbohydrate for a few days, or return to normal eating after a period of eating less, and the scale may rise before much long-term fat storage has changed. The body may simply be refilling its short-term fuel tanks, and those tanks are wet. They are not dry shelves. They are more like soft sponges, holding stored glucose and water together inside muscle and liver tissue. This also works in the other direction. If the body uses a lot of glycogen during exercise, illness, fasting, or lower carbohydrate intake, some of the water stored with it may leave too. The scale can drop quickly, but that quick drop does not always mean a large amount of fat has disappeared. It may mean stored carbohydrate and water have shifted. This makes body weight more fluid than it appears. The number may look exact, down to a single pound, or even a decimal point. But inside the body, the number is moving with stored fuel, water, salt, digestion, inflammation, and daily rhythm. Glycogen shows us that early weight gain can be more subtle than it seems. It may not begin with fat cells growing larger. It may begin with glucose being tucked into liver and muscle. It may begin with water following that glucose into storage. It may begin with the body preparing for movement, fasting, sleep, and the hours between meals. Before long-term storage becomes part of the story, the body first fills this quieter reserve. A short-term supply, a useful supply, a supply that can change quickly and make the body feel heavier or lighter as water gently follows fuel. Because glycogen holds water, the body can become heavier before it has gained much lasting tissue. This is one of the gentlest and most useful truths in the science of weight. The scale can rise even when the main thing changing is fluid. Water is not just something the body drinks and releases. It is part of the blood. It fills the spaces inside cells. It moves between tissues. It helps carry nutrients. It helps control temperature. It cushions joints. It moistens the eyes, mouth, nose, and digestive tract. An adult human body is often more than half water, though the exact amount depends on age, body size, sex, and body composition. A baby's body contains an even higher share of water. An older adult's body usually contains less. So when body water shifts, body weight can shift too. Not because the body has suddenly changed its long-term storage, but because water is always moving. Some water travels inside blood vessels, carried with red blood cells, minerals, glucose, proteins, and hormones. Some water rests inside cells, where thousands of chemical reactions happen every second. Some water sits in the space between cells, like a quiet fluid cushion around living tissue. And some water is inside the digestive tract, mixed with food, stomach juices, bile, and the fluids released by the intestines. After a salty meal, the body may hold more water for a while. Salt contains sodium, and sodium helps control fluid balance. When more sodium enters the body, water often follows it, helping keep the concentration of the blood within a safe range. This is why a meal of soup, pizza, salted snacks, takeout food, cured meat, or restaurant food can sometimes make the body feel heavier or puffier the next day. The body is not failing. It is diluting and balancing. It is trying to keep the blood stable. Heat can shift water too. On a warm summer day, sweat carries water and salt to the surface of the skin. As sweat evaporates, it helps cool the body. If water is lost through sweating and not fully replaced, weight may drop for a short time, but that drop is mostly fluid. When the person drinks and eats again, much of that weight can return. Inflammation can also bring water into tissues. Inflammation is the body's repair response. It can happen after a hard workout, a minor injury, an infection, or even after muscles do work they are not used to. tiny blood vessels may become more open, allowing fluid and immune cells to move into the area. That swelling is part of healing. A sore muscle after a long hike, a swollen ankle after a twist, or a tender arm after lifting something heavy may all hold extra fluid for a while. Hormones can change water balance as well. The kidneys respond to hormones that tell them how much water and sodium to keep or release. One of these hormones is called antidiuretic hormone, which helps the body hold water when it needs to. Another system, involving the kidneys and adrenal glands, helps manage sodium and blood pressure. In many people, monthly hormone changes can also affect fluid retention, making weight rise and fall across the cycle. Digestion adds its own quiet layer. A large meal has physical weight before it is absorbed. Fiber-rich foods can hold water inside the gut. The intestines may contain food in different stages of digestion for many hours. A meal eaten in the evening can still be part of the body's measured weight the next morning. This is why a few pounds can appear or disappear over days. Water can move into muscle with glycogen. It can follow sodium. It can gather around healing tissue. It can leave through sweat. It can sit inside the gut. It can shift between the blood, cells, and spaces around cells. The scale may show one number, but that number is not a pure measure of fat. It is more like a photograph taken of a river. For one instant, the river has a shape, but the water is still flowing. Body weight is like that. It looks fixed when seen as a number, but inside, it is moving with fluid, minerals, food, stored carbohydrate, hormones, heat, and repair. This temporary layer matters because it can hide the slower story underneath. Water can rise quickly. Water can fall quickly. But if extra energy continues arriving after the body has filled its short-term stores, the body turns toward a deeper reserve. A storage system built not for hours, but for weeks, months, and sometimes years. When the temporary layer of water begins to settle, the deeper storage system comes into view. This system is built around fat cells. Fat cells are also called adipocytes. They are small living cells designed to hold energy in a compact form. Inside many fat cells is a large droplet of stored fat. That droplet is made mostly of molecules called triglycerides. A triglyceride is built from 3 fatty acids attached to a smaller backbone called glycerol. The name itself gives a clue. Tri means 3. Glyceride points to glycerol. So a triglyceride is, in simple terms, 3 fat chains held together on one small frame. This shape makes it excellent for storage. It is dense, it is stable, and it can hold a large amount of energy in a small space. Carbohydrate and protein each provide about 4 calories of energy per gram. Fat provides about 9 calories per gram. That means fat stores more than twice as much energy in the same weight. For a body trying to survive across uncertain days, this matters. If the body stored all its backup energy as carbohydrate, it would need far more space and far more water. Glycogen is useful, but it is bulky because water comes with it. Fat is different. It can be stored with much less water, tucked into cells beneath the skin and around certain organs. You can picture fat storage like a quiet pantry, but one built inside living tissue. not a shelf made of wood, not a jar with a label. A soft biological reserve, held in round cells, supplied by blood vessels, watched by hormones, and ready to be opened when the body needs fuel. This system did not appear by accident. It is ancient. Animals store fat because the natural world has never offered food on a perfect schedule. A bear builds fat before winter. A whale calf depends on rich milk and stored energy while growing in cold water. Migrating birds can double their body fat before long flights because fat is light enough and energy-rich enough to carry across oceans and deserts. Humans are part of this same living pattern. For most of human history, food could not be ordered, refrigerated, frozen, or shipped across continents in a few days. Homo sapiens have existed for roughly 300,000 years. Farming began much later, around 12,000 years ago in several parts of the world. Modern grocery stores, electric refrigerators, drive-through meals, and 24-hour food access are extremely recent when compared with the age of the human body. For the body, saving energy was not a flaw. It was protection. A person with stored fat could better survive a poor harvest, a long walk, an illness, a cold season, or days when hunting and gathering produced very little. Stored fat also helps support pregnancy and breastfeeding, which require large amounts of energy. It helped keep the body warm. It helped protect organs. It gave the body a reserve when food was scarce or appetite was low. So when extra energy keeps arriving after immediate needs are met, the body has a place to put it. Fat cells can take in fatty acids from the blood. They can also store energy that began as extra carbohydrate after the body has changed it through several steps. The liver plays a role in this sorting. Insulin helps signal that fuel is available. Blood vessels deliver the building materials. Then, fat cells package energy into triglycerides and hold it quietly. This is long-term storage. Not storage for the next few hours. Not just a small reserve for a walk after dinner, but storage that can remain for weeks, months, or much longer if the body does not need to draw it down. And because fat holds so much energy in such a small form, the body treats it carefully. It does not waste it easily. It does not forget it is there. It keeps track of it through hormones, nerves, blood flow, and chemical signals. This makes weight gain easier to understand in a calmer way. The body is not confused when it stores fat. It is using a survival system older than cities, older than written language, older than farming, and far older than the modern food world surrounding it now. The deeper question is not why the body stores energy. It is why such a useful system can become so persistent once it begins to fill. Once long-term storage begins, fat cells can change their shape. They do not stay fixed like pebbles under the skin. They are living cells, and living cells can respond to what is happening around them. A fat cell is also called an adipocyte. Under a microscope, a white fat cell often looks like a tiny round bubble. Most of its inside space is taken up by one larger droplet of stored triglyceride. The rest of the cell is pushed toward the edge. Its nucleus, the part that holds genetic instructions, sits off to the side like a small moon pressed against the rim. This is one reason fat cells can look so simple at first glance. They appear soft, pale, and round. But they are not empty containers. They are alive. They have membranes. They have receptors. They receive oxygen and nutrients from nearby blood vessels. They respond to insulin. They release signals into the blood. And when more energy is stored inside them, they can grow larger. This kind of growth is called hypertrophy. Hypertrophy simply means a cell gets bigger. In fat tissue, this happens when a fat cell stores more triglyceride inside its central droplet. The cell expands slowly, like a small balloon filling with oil instead of air. It may start out modest in size, then become much larger as stored energy increases. Different fat cells can expand by different amounts, depending on where they are in the body, how well blood reaches them, and what signals are present in the tissue around them. Fat tissue also exists in more than one place. Some fat is stored under the skin. This is called subcutaneous fat. Subcutaneous means beneath the skin. It can be found around the hips, thighs, arms, abdomen, back, and other areas. Some fat is stored deeper inside the belly, around organs. This is called visceral fat. Visceral means related to the internal organs. These two storage areas can behave differently. They may release different signals. They may respond differently to hormones. They may have different effects on the body's chemistry. So even the location of stored fat matters. Weight gain is not just a layer becoming thicker. It is a living tissue changing in different regions of the body. Fat cells can also increase in number. This is called hyperplasia. Hyperplasia means more cells are made. The body can create new fat cells when existing cells become too full, or when growth signals encourage new storage space. This can happen more easily during certain life stages, such as childhood, puberty, and pregnancy. During childhood, the body is still building many tissues, and fat cell number can rise as part of normal growth. During puberty, hormones shift the way the body stores fat and muscle. During pregnancy, the body changes storage patterns to support the growing baby, and later milk production. In adulthood, the number of fat cells is often more stable than their size. Fat mass can rise or fall as existing fat cells grow or shrink. The cells themselves may remain. They may simply hold more or less triglyceride. This helps explain why fat tissue has memory-like qualities. Not memory in the way the brain remembers a song or a face, but a kind of biological history. The tissue has structure. It has cell number. It has blood vessels. It has immune cells nearby. It has signals that have been shaped over time. Inside growing fat tissue, blood supply becomes important. Every living cell needs oxygen. Every living cell needs a way to receive nutrients and remove waste. As fat tissue expands, tiny blood vessels must support it. If a fat cell grows very large, oxygen may not reach every part of the tissue as easily. The body may respond by calling in immune cells and changing local signals. This is one reason fat tissue is active, not silent. It is constantly being watched, supplied, repaired, and adjusted. A fat cell also has receptors on its surface. A receptor is like a tiny listening point. It allows the cell to respond to messages in the blood. Insulin can tell fat cells that energy is available. Stress hormones can tell fat cells to release some stored fuel. Other hormones can change how easily fat is stored or used. The cell is listening all the time. So when fat cells grow, they do more than take up space. They change the conversation. Larger fat cells may release different amounts of chemical signals. The tissue around them may become busier. The brain may receive stronger messages about stored energy. The blood may carry a different mix of hormones and inflammatory signals. And slowly, what began as storage becomes communication. The body has not only saved energy, it has changed the voice of one of its own organs. And as those fat cells speak more loudly, the brain begins listening more closely. As fat cells grow, their message to the body changes. They do not speak with sound. They speak with hormones. A hormone is a chemical messenger that travels through the blood, carrying information from one tissue to another. One of the most important hormones made by fat cells is called leptin. Leptin was identified in the 1990s after scientists studied a gene involved in body weight regulation in mice. Its name comes from a Greek word linked to thinness. But leptin is not a simple thinness hormone. It is more like an energy report. It helps tell the brain how much stored energy the body has available. When fat cells are larger, they usually release more leptin. When fat stores become smaller, leptin levels often fall. This creates a quiet signal between adipose tissue and the brain. A soft message moving through the blood. A report from the storage tissue beneath the skin and around the organs. The brain listens to this message because the brain is always watching energy. It has to. The brain cannot safely run out of fuel. Even at rest, it uses a large share of the body's daily energy, and it depends on a steady supply of glucose and oxygen from the blood. So it pays close attention to signals that describe hunger, fullness, stored fuel, stress, body temperature, and recent meals. Leptin is part of that larger monitoring system. It can act on an area deep inside the brain called the hypothalamus. The hypothalamus is small, about the size of an almond, but it helps control many basic survival functions: hunger, thirst, body temperature, sleep rhythms, hormone release, energy balance. It sits below the larger thinking parts of the brain, quietly managing the body's internal state. When leptin reaches this region, it helps inform the brain that stored energy is present. In a simple version of the story, more leptin should mean the body knows it has more stored fuel. Less leptin should mean stored fuel is lower, and the body may increase hunger or conserve energy. But the body is rarely simple. In many people with higher amounts of fat tissue, leptin levels can also be higher, yet the brain may not respond to that signal as strongly as expected. This is sometimes called leptin resistance. Resistance means the message is present, but the response is weaker. It is a little like a radio signal reaching a receiver through static. The signal exists, but the brain may not hear it clearly enough to fully change hunger or energy use. This helps explain why body weight is not controlled only by conscious choice. A person does not simply decide hunger into silence. The brain is receiving constant updates from the stomach, intestines, pancreas, liver, muscles, band tissue, and blood. Some signals say food has arrived. Some say the stomach is stretching. Some say blood sugar is rising. Some say stored energy is available. Some say the body is tired. Some say stress is high. Some say it is night and the body should be resting. Together, these signals shape appetite, cravings, fullness, and energy use before a person has even lifted a fork. Fat tissue is part of that conversation. It sends leptin. It sends adiponectin, which helps influence how the body handles sugar and fat. It releases other chemical signals too, some involved in inflammation and repair. So adipose tissue is not silent padding. It is a living organ of storage and communication. It gives the brain information about the body's reserves, and the brain uses that information to help decide whether to seek food, conserve energy, release fuel, or keep the body steady. This makes weight gain feel less like a single outside change and more like a shifting internal dialogue. Fat cells store energy. Then they report that stored energy. The brain receives the report. Then it blends that report with many others, from the gut, the blood, the muscles, and the rhythms of the day. Leptin is one important voice in that quiet system. But it is not the only one. Another strong signal arrives soon after eating, when fuel enters the blood and the body begins deciding where that fuel should go. After a meal, the bloodstream begins to change. Carbohydrates that were once bread, fruit, rice, beans, potatoes, or oats have been broken down into glucose. Glucose is a simple sugar. It is one of the body's main fuels. A little glucose is always needed in the blood because many cells depend on it, and the brain uses it steadily throughout the day and night. But blood glucose has to stay within a safe range. Too little can leave the body weak, shaky, and confused. Too much for too long can damage delicate blood vessels and tissues. So when glucose rises after eating, the body responds quickly. One of the main organs involved is the pancreas. The pancreas sits deep in the upper abdomen, tucked behind the stomach. It is only about 6 inches long, but it has a powerful role in digestion and blood sugar control. Some parts of the pancreas release digestive juices into the small intestine. Other parts release hormones directly into the blood. One of those hormones is insulin. Insulin is often talked about as if it is only connected to weight gain. But insulin is not bad. It is essential. Without insulin, glucose would have a much harder time moving from the blood into many of the cells that need it. Insulin works like a signal. After blood glucose rises, the pancreas releases insulin into the bloodstream. Insulin then travels through the body and tells certain cells that fuel is available. Muscle cells can respond by letting more glucose in. Fat cells can respond too. The liver also listens closely. You can picture insulin not as a harsh command, but as a soft knock at the door. A message saying, "Fuel has arrived. Please take what you need." In muscle and fat cells, insulin helps move special glucose transporters toward the cell surface. A transporter is like a tiny doorway that allows glucose to enter. When more of these doorways appear, glucose can move out of the blood and into the cell. Inside muscle cells, some glucose may be burned for energy. Some may be stored as glycogen. the short-term carbohydrate reserve. Inside the liver, glucose can also be packed into glycogen. This helps explain why insulin is connected to storage. When energy is available, insulin helps the body save some of it. That saving is not a mistake. It keeps blood sugar from rising too high. It gives the liver fuel to release later. It gives the muscles fuel for movement. It helps the body prepare for the quiet hours between meals. If glycogen stores are already full and more energy keeps arriving, the body has other ways to handle it. The liver can transform some extra fuel into fat. Fat cells can take in fatty acids and store them as triglycerides. Insulin helps support this storage state, especially when the body is well fed. It also slows the release of stored fat for a while, because the body usually burns incoming fuel before it opens its deeper reserves. This makes sense from the body's point of view. If fresh fuel has just arrived in the blood, there is less need to pull fuel out of long-term storage at the same moment. The body shifts toward using and saving what has come in. Then, later, as insulin falls between meals, stored fuel can become easier to release again. This rise and fall happens every day. Breakfast may raise insulin. A midday meal may raise it again. An evening meal may bring another wave. The pattern depends on the type of food, the size of the meal, recent movement, sleep, stress, and how sensitive the cells are to insulin's message. Insulin sensitivity means how well cells respond to insulin. When cells are very sensitive, a smaller amount of insulin can help move glucose where it needs to go. When cells are less sensitive, the pancreas may need to release more insulin to get the same job done. This is not a simple switch. It can change with sleep, activity, body composition, genetics, age, and health. So insulin is not the villain of weight gain. It is part of a careful fuel management system. It helps keep the blood steady. It helps cells receive energy. It helps the liver and muscles store glycogen. It helps fat cells store extra fuel when more energy is available than the body needs right away. Weight gain does not come from one hormone acting alone. It comes from many signals lining up over time. Food entering the blood, insulin rising, cells receiving fuel, storage spaces filling, hunger changing, sleep shifting, stress rising or falling, movement using or sparing energy. The body listens to all of it, quietly sorting what should be burned now, what should be stored briefly, and what should be saved for later. Hunger can feel as if it begins in the stomach, a hollow feeling, a soft tightening, a little sound from the belly in a quiet room. But the stomach is only one voice in the body's hunger system. The feeling of hunger is built from signals moving between the stomach, intestines, pancreas, fat tissue, blood, and brain. Some signals are physical. The stomach stretches when food enters it. As it empties, that stretch fades. Other signals are chemical. Hormones rise and fall. Glucose moves through the blood. Fatty acids appear after digestion. Amino acids arrive from protein. The brain reads all of this together, like a weather station reading pressure, wind, clouds, and temperature before predicting rain. One of the best-known hunger signals is called ghrelin. Ghrelin is a hormone made mostly in the stomach. It tends to rise before meals, when the stomach has been empty for a while. Then it usually falls after eating. This is why ghrelin is often called a hunger hormone. It does not create hunger all by itself, but it helps turn the volume up. It sends a message toward the brain that food may be needed soon. You can picture ghrelin rising gently before breakfast, after the long overnight fast. The stomach is quieter. The blood has been managed through the night. The liver has released stored glucose to help keep the brain supplied. And as morning arrives, ghrelin may begin to climb, nudging the body toward food. But hunger is not only about being empty. The intestines also speak after food arrives. When nutrients enter the small intestine, specialized cells in the gut release hormones that help tell the brain that digestion is underway. One of these hormones is called CCK, short for cholecystokinin. It helps slow stomach emptying and supports the release of bile and digestive enzymes. Another is GLP-1, which helps the body respond to incoming glucose and can support feelings of fullness. Another is peptide YY, often called PYY, which tends to rise after eating and helps reduce appetite for a while. These names may sound technical, but their job is simple to understand. They are part of the body's meal report. Food has arrived. Nutrients are being absorbed. Slow down. There is no need to keep searching right now. The pancreas joins the conversation too. After carbohydrates are digested into glucose, the pancreas releases insulin. Insulin helps move glucose from the blood into cells. But insulin also tells the brain and other tissues that fuel is available. Fat tissue adds its own longer-term signal through leptin. Leptin gives the brain information about stored energy. So hunger is shaped by both short-term meal signals and longer-term storage signals. The stomach may say it is empty. The gut may say food has arrived. The pancreas may say glucose is rising. Fat tissue may say energy is stored. The brain has to blend all of it. This is why hunger can feel different on different days. A meal high in protein and fiber may stay in the stomach longer and trigger stronger fullness signals. Beans, lentils, oats, vegetables, eggs, yogurt, fish, or meat can affect hunger differently than a sweet drink or a soft, refined snack that moves through the stomach more quickly. Food texture matters too. Liquid calories often create less lasting fullness than solid food, partly because they leave the stomach faster and require less chewing. Chewing itself gives the body time. It lets taste, smell, stretch, and gut hormones begin lining up before more food arrives. Routine matters as well. If a person eats lunch every day at noon, the body may begin preparing before noon arrives. Saliva increases. Stomach activity shifts. Hunger hormones may follow the learned rhythm. The body remembers patterns, not with thoughts, but with repeated chemistry. Sleep can change the pattern. After a short night, hunger may feel stronger. Food may seem more rewarding. Stress can change it too. Some people lose appetite during sudden stress. Others feel more pull toward familiar, energy-rich foods during long-lasting stress. Neither response is strange. Both show that hunger belongs to the whole body, not just the stomach. So when hunger appears, it is not a simple empty signal. It is the brain interpreting messages from deep inside the body. Stretch, glucose, hormones, stored energy, meal timing, sleep, stress, memory. And as all those quiet signals arrive together, the brain begins deciding what the body needs, what it expects, and what it may ask for before the first bite is even taken. The brain does not receive hunger as one simple message. It receives a stream of information. Some of it comes from the stomach. Some comes from the intestines. Some comes from the liver, pancreas, muscles, blood, and fat tissue. And deep inside the brain, one small region helps gather many of these signals into a survival plan. This region is called the hypothalamus. It is small, only about the size of an almond, and it sits near the base of the brain. Yet it helps manage some of the body's most basic needs: hunger, thirst, body temperature, sleep rhythms, hormone release, energy balance. The hypothalamus is not the thinking, planning part of the brain. It does not count meals or read labels or make a grocery list. It works more quietly than that. It listens to the body. It watches the blood. It responds to hormones. It helps decide whether the body should feel hungry, conserve fuel, release heat, hold water, or prepare for rest. One of its main jobs is stability. The scientific word for this is homeostasis. Homeostasis means keeping the body's internal conditions within a safe range. Blood glucose should not drift too high or too low. Body temperature should stay near its usual range. Water and salt should stay balanced. Blood pressure should not swing wildly. The body survives by keeping many things steady, even while the outside world keeps changing. A person may sleep in a cool room, walk outside on a hot day, eat a salty meal, skip lunch, climb stairs, catch a cold, or feel stress before an appointment. Through all of it, the brain and body keep adjusting. The hypothalamus is part of that quiet adjustment system. When the body has recently eaten, the brain receives signals that fuel is arriving. Glucose rises. Insulin appears. The stomach stretches. Gut hormones begin to speak. Fat tissue sends longer-term signals about stored energy. When the body has gone hours without food, the signal pattern changes. The stomach empties. Ghrelin may rise. Blood fuel may shift. The liver may release stored glucose. The brain does not read these signals one by one, like separate notes on a page. It blends them. It compares what is coming in with what is already stored. It compares today with familiar patterns from yesterday, last week, and many repeated routines before that. This is one reason the body can learn meal timing. If food usually arrives at the same hour, the body may begin preparing ahead of time. Digestive juices may increase. Hunger may appear before the meal is even seen. The body is not only reacting, it is predicting. This ability is useful. A body that can predict food, cold, danger, movement, and rest can prepare more smoothly. But it also means the body can resist sudden change. Stability is safer than chaos. If energy intake drops sharply, the brain may respond by increasing hunger and reducing energy use. If sleep becomes short, food signals may become louder. If stress stays high, appetite and storage signals may shift. If weight has been higher for a long time, the body may begin treating that state as familiar. Not ideal, not chosen, just familiar. The body often protects what it knows. This does not mean change is impossible. It means change is biological. It has to move through systems that were built to prevent sudden loss, sudden shortage, and sudden instability. For most of human history, losing stored energy quickly could have meant danger, a long winter, a failed harvest, an illness, a journey with little food. A body that fought to protect its reserves had a better chance of surviving. So the brain became careful. It learned to watch stored energy closely. It learned to notice when fuel was low. It learned to defend against sudden drops. And in the modern world, that ancient care can make weight gain easier to hold than many people expect. The brain is not simply watching the body from above. It is part of the body's storage system. It listens to hormones. It remembers patterns. It protects stability. And once a new pattern has lasted long enough, the body may begin treating it as the new normal, quietly shaping hunger, energy use, and storage around the state it has come to know. Once the brain begins treating a body state as familiar, daily routines start to matter in a quiet way. The body does not only respond to what happens once, it responds to what happens again and again. A meal at the same hour, a snack in the same chair, coffee at the same desk, a late night after the same kind of stressful day, a sweet taste after dinner, a long stretch of sitting before sleep. Each event may seem small on its own, but the body is very good at learning patterns. It learns the rhythm of morning light. It learns when food usually arrives. It learns when movement usually happens. It learns when the day becomes quiet. And over time, those repeated signals can shape hunger, cravings, digestion, and energy use. This learning is not only psychological, it is biological. Before a regular meal, the mouth may begin making more saliva. Saliva contains water, minerals, mucus, and digestive enzymes. Its job is to moisten food, begin digestion, and help swallowing happen smoothly. The stomach may also begin preparing. It can increase movement and release digestive juices before food has even arrived. This is sometimes called the cephalic phase of digestion. Cephalic means related to the head. It describes the way the sight, smell, thought, or expectation of food can start digestion early. A familiar kitchen smell can do this. The sound of a wrapper can do this. The sight of a usual dinner plate can do this. Even the time of day can become a signal. If lunch usually happens around noon, hunger may begin to appear around noon. Not because the stomach has checked a clock, but because the body has learned the rhythm. Hormones can follow patterns too. Ghrelin, the hunger-related hormone, made mostly in the stomach, often rises before expected meals. If meals happen at regular times, ghrelin may begin climbing before those times arrive. The body is preparing the person to eat before the first bite. This is useful when life is steady. It helps digestion happen smoothly. It helps the body receive food with less surprise. but it also shows how hunger can be trained by routine. Cravings can be shaped in a similar way. A craving is not always simple hunger. It can be memory, reward, smell, texture, emotion, and habit all arriving together. The brain remembers foods that brought quick energy or comfort. Soft bread, sweet cereal, salty chips, warm fries, creamy desserts, sweet drinks. These foods are not powerful only because of calories. They are powerful because taste, smell, texture, and memory are tied to reward pathways in the brain. A reward pathway is a group of brain circuits that help the body notice what feels useful, pleasurable, or worth repeating. This system helped humans remember ripe fruit, safe foods, nourishing meals, and social eating. But in a modern home, car, office, or grocery store, those same circuits can be triggered many times a day. A routine can slowly become a path. The body walks it often enough that it begins to feel natural. After dinner, the body may expect sweetness. During a long workday, it may expect a snack at a certain hour. After poor sleep, it may ask for quicker energy. After stress, it may search for foods that feel familiar and easy. Digestion also learns. The gut has its own nervous system, sometimes called the enteric nervous system. It contains hundreds of millions of nerve cells spread through the digestive tract. These nerves help control squeezing motions, enzyme release, blood flow, and the movement of food. The gut is not thinking like the brain thinks, but it is sensing and adjusting all the time. It knows when food stretches the stomach. It senses nutrients in the small intestine. It helps send messages upward through nerves and hormones. Repeated routines can shape this whole pattern. Weight gain can happen the same way, not always as one dramatic change, not always from one meal, 1 week, or one decision. More often, it can grow from repeated signals that become familiar. A little more energy arriving than the body uses. A little less movement across the day. A little less sleep. A little more stress. A regular craving at night. A regular meal eaten quickly. A regular drink that adds energy without much fullness. Each piece may be small, but the body does not experience life as isolated pieces. It experiences patterns. And when a pattern repeats for weeks, months, or years, the body may begin organizing itself around it. Hunger arrives at expected times. Storage signals repeat. Energy use adjusts. Digestive rhythms settle into their usual path. What looks like one change from the outside may actually be hundreds of small signals, becoming familiar inside. And because every body has its own size, muscle, age, genes, sleep, history, and rhythm, those patterns do not affect everyone in the same way. Because patterns affect each body differently, metabolism cannot be understood as one simple speed. People often talk about metabolism as if it is a small fire inside the body. Fast for some, slow for others. But metabolism is not one flame. It is every chemical process the body uses to stay alive. It is the heart using fuel to beat, the liver sorting nutrients, the kidneys filtering blood, the brain sending electrical signals, the muscles repairing tiny fibers after movement, the skin renewing itself, the stomach and intestines breaking down food, the body warming itself in a cool room. All of this is metabolism. Even sleep has a metabolism. During rest, the body still uses energy to keep breathing steady, move blood, regulate temperature, release hormones, repair tissue, and keep cells alive. This resting energy use is often called resting metabolic rate. It means the amount of energy the body uses while awake, still, calm, and not digesting a recent meal. For many people, resting energy use is the largest part of daily energy use. Not exercise, not a workout, not a walk through the grocery store, just staying alive. The heart, brain, liver, kidneys, and other organs are busy tissues. They are small compared with the whole body, but they use a large share of energy. The liver alone carries out hundreds of jobs, from storing glycogen to processing fats, handling amino acids, and breaking down old blood products. The kidneys filter huge amounts of fluid each day. The brain, though only about 2% of body weight, uses about 1/5 of resting energy, so a body lying quietly in bed is still active beneath the surface. Warm blood moves through vessels. Cells build and break molecules. The lungs rise and fall. The body is spending energy without making any visible effort. Digestion also uses energy. After a meal, the body must chew, churn, dissolve, absorb, transport, and sort the food that entered. This is sometimes called the thermic effect of food. Thermic means related to heat. Food does not pass through the body without cost. Protein usually takes more energy to digest and process than carbohydrate or fat. That does not make one food magical. It simply shows that different nutrients require different kinds of work. Movement adds another layer. A planned walk, a bike ride, or a workout uses energy. But so does standing, folding laundry, tapping a foot, carrying a bag, walking upstairs, cleaning a counter, or shifting posture in a chair. These small movements can vary a lot from person to person. One person may sit very still for hours. Another may stand often, pace while talking, walk to errands, or move around the house without thinking about it. Across a whole day, those quiet differences can add up. Body size matters too. A larger body usually needs more energy to move and maintain than a smaller body. Lean mass matters. Lean mass includes muscle, organs, bone, and other non-fat tissue. Muscle is not the only energy-using tissue, but it does use energy even at rest, and it becomes especially important during movement. Age matters as well. Children and teenagers use energy for growth. Adults use energy for maintenance and repair. As people get older, muscle mass may decline if it is not maintained, and this can change daily energy needs. Hormones influence metabolism too. Thyroid hormones help set the pace of many body processes. The thyroid gland sits in the front of the neck, shaped a little like a butterfly. When thyroid hormone levels are lower than normal, many body processes may slow. When they are higher than normal, many processes may speed up. Sex hormones, stress hormones, insulin, and leptin also help shape how the body uses and stores energy. Genes add another layer. Two people can have different hunger signals, different body sizes, different muscle amounts, different sleep patterns, different movement habits, and different hormone responses. They may eat similar meals and live similar days, yet their bodies may not spend energy in exactly the same way. This is why metabolism is not a single number stamped onto a person. It is more like a whole city at night. Some buildings are brightly lit. Some streets are quiet. Some systems run all the time, like hospitals, water pumps, and power stations. Others wake and slow with the rhythm of the day. Inside the body, the brain, liver, heart, kidneys, muscles, fat tissue, gut, and hormones all take part in that living city. Energy moves through it constantly. Some is spent. Some is stored. Some is lost as heat. Some is used to repair what the day has worn down. And because no two bodies are built, shaped, moved, rested, stressed, or fed in exactly the same way, weight gain does not unfold identically from person to person. Because metabolism is made of many moving parts, two bodies can never be perfect copies of each other. Even when two people eat similar meals, even when they walk the same hallway, even when they live in the same home, sleep under the same roof, and follow the same daily schedule. The body is not a machine built from one standard design. It is a living history. It carries genes from parents and grandparents. It carries childhood growth patterns. It carries muscle, bone, hormones, sleep habits, stress responses, medications, illnesses, and routines repeated over many years. Genetics can influence appetite. Some people naturally feel full sooner. Some feel hunger more strongly. Some may be more sensitive to food reward, smell, texture, or sweetness. Some may store energy more easily in certain areas of the body. These differences are not signs of character. They are differences in biology. Genes help shape the way the brain responds to hunger hormones. They can affect how quickly fullness appears after a meal. They can influence body size, fat distribution, insulin sensitivity, and how the body uses energy at rest. Human genetics is not destiny, but it is part of the landscape. It sets some of the slopes the body has to walk across. Body composition matters too. Body composition means what the body is made of. Muscle, fat, bone, organs, water, connective tissue. Two people can weigh the same amount and have very different bodies inside. One may carry more muscle. Another may carry less. One may have a larger frame. Another may have smaller bones. One may have more active daily movement. Another may sit still for long stretches. Muscle tissue uses more energy than fat tissue, even at rest. It is not a huge roaring furnace, but it is more metabolically active. A pound of muscle needs more energy to maintain than a pound of fat. Muscle also stores glycogen and helps pull glucose out of the blood after meals. This means muscle changes the way the body handles fuel. The large muscles of the legs, back, chest, and hips can act like storage places for short-term carbohydrate. After movement, those muscles may become more ready to take in glucose and rebuild their glycogen supply. This is one reason body composition shapes weight change. It affects not only how the body looks from the outside, but how fuel moves inside. Hormones add another layer. Thyroid hormones help set the pace of many body processes. Insulin helps move glucose into cells. Cortisol helps the body respond to stress. Estrogen and testosterone influence muscle, fat distribution, appetite, fluid balance, and tissue repair. Hormones shift during puberty, pregnancy, postpartum recovery, menopause, aging, illness, and periods of stress. A body going through a hormone change may store water differently. It may feel hungrier. It may use energy differently. It may gain weight more easily, even if the person has not changed much on purpose. Some medical conditions can also make weight gain more likely. An underactive thyroid can slow many body processes. Polycystic ovary syndrome, often called PCOS, can affect insulin, hormones, and fat storage. Cushing syndrome, which involves high cortisol levels, can change body fat patterns. Long-term pain, injury, or fatigue can reduce movement, which changes daily energy use. Even poor sleep from sleep apnea can affect hunger signals, stress hormones, and blood sugar control. Medications can matter as well. Some antidepressants, antipsychotics, steroids, seizure medicines, diabetes medicines, and hormonal treatments can increase appetite, change fluid balance, or shift the way the body stores energy. This does not make those medicines bad. Many are necessary and helpful. It simply means weight can change for reasons that are not visible from the outside. A person may not be eating more in an obvious way. They may not be moving less by choice. Their body chemistry may have changed quietly through treatment, illness, hormones, or recovery. This is why weight gain should be understood gently. From the outside, it may look like one simple change. Inside, it may involve genes, muscle, thyroid signals, sleep, medications, stress, blood sugar, movement, appetite, and the body's long memory of repeated routines. The equation is real because energy still has to come from somewhere and go somewhere. But the body deciding how hungry it feels, how much energy it spends, how much water it holds, and where it stores fuel is deeply personal. Weight gain is not just arithmetic written on the body. It is a landscape, and every body has its own hills, rivers, weather, seasons, and hidden paths. Once that becomes clear, the story expands beyond the individual body and into the world that body has to live inside. Once the body is seen as its own landscape, the world around it becomes part of the story. A body does not gain weight in empty space. It lives in kitchens, bedrooms, offices, cars, classrooms, stores, streets, and glowing rooms after dark. It lives inside schedules. It lives inside habits. It lives inside a food environment that has changed much faster than biology can change. Human bodies are ancient. Homo sapiens have existed for roughly 300,000 years. For most of that time, food required effort. People gathered plants, dug roots, cracked nuts, hunted animals, carried water, walked long distances, and moved with the seasons. Food could be abundant for a while, then scarce. A fruit tree ripened and then passed. A herd moved away. A winter came. A drought changed the land. A body that could store extra energy had a real advantage. Stored fat was not a problem in that older world. It was a reserve. It helped bridge the quiet space between one meal and another. It helped protect the body during illness, travel, cold weather, pregnancy, and breastfeeding. Then the world changed. Farming began about 12,000 years ago, which sounds ancient, but it is recent compared with the age of our species. Cities, grain storage, trade routes, mills, ovens, and markets slowly changed how humans found food. Then the changes became faster. Canned food spread widely in the 19th century. Electric refrigerators became common in homes during the 20th century. Supermarkets grew larger. Food could be frozen, shipped, boxed, flavored, preserved, advertised, and delivered. Now, in many places, food is available in the morning, at midnight, at a gas station, from a phone, from a vending machine, or from a bright store aisle lined with hundreds of packages. The body still carries an older storage system, but that system now lives in a world of constant access. Movement changed too. For most of human history, daily life required walking, lifting, carrying, squatting, climbing, digging, washing, building, and gathering. Today, many people can spend hours sitting in a chair, moving only their hands across a keyboard, a steering wheel, or a phone screen. A car can replace a long walk. An elevator can replace stairs. A washing machine can replace hours of hand washing. A desk can hold the body still through most of the day. None of these changes are bad by themselves. They are part of comfort, safety, work, and modern life. But they mean the body may receive more energy while spending less through ordinary movement. Artificial light adds another quiet layer. For most of human history, the sun shaped the day. Morning light signaled waking. Darkness signaled rest. Firelight was dim compared with modern bulbs and screens. Now bright indoor light can stretch the day deep into the night. Phones, televisions, laptops, streetlights, and store signs can keep the brain alert long after sunset. When sleep becomes shorter or later, hunger hormones, food reward, stress signals, and blood sugar control can shift. The body receives the same world through a more tired chemistry. Stress has changed shape as well. Instead of running from a predator or facing a short physical danger, modern stress may come from bills, deadlines, traffic, messages, noise, social pressure, caregiving, school, work, or uncertainty that lasts for weeks. The stress system was built to help the body respond to challenge. But when challenge becomes constant, appetite, sleep, digestion, and energy use can all be affected. Modern food itself can be especially easy to store. Many foods are soft, quick to chew, rich in fat, sugar, starch, and salt, and easy to eat quickly. They may combine sweetness, creaminess, crunch, and salt in ways the brain finds rewarding. This does not make the body weak. It shows that old reward systems are meeting a new kind of food world. A ripe berry in a forest once gave sweetness with water, fiber, and effort. A sweet drink can deliver energy quickly, with little chewing and less fullness. A handful of nuts once had to be gathered and cracked. Today, energy-rich foods can sit ready in a bag beside the couch. The storage system has not failed. It is doing what it was shaped to do. It notices available fuel. It saves what is not needed right away. It prepares for a shortage that may never come. The body is ancient, careful, and protective. The modern world is bright, convenient, stressful, and full. And where those two meet, The old storage system can be asked to handle more than it was ever meant to handle quietly. When the modern world offers food everywhere, the kind of food matters too. The body does not respond only to fuel. It also responds to pleasure. A warm smell from a bakery, the crisp snap of a chip, the soft texture of ice cream, the salt on fries, the sweetness of a drink, the creamy feeling of melted cheese. These details are not separate from biology. They are biology. The brain is built to notice food that is rich, safe, and worth finding again. For most of human history, this was useful. Sweetness could mean ripe fruit. Fat could mean dense energy. Salt could mean minerals the body needed. Softness could mean food that was easy to chew and digest. A strong smell could help a person find food before seeing it. The brain learned to mark these things as important. One chemical involved in this marking is dopamine. Dopamine is often described as a pleasure chemical, but it is more than that. It helps the brain notice reward, remember it, and seek it again. When a food feels especially pleasant, dopamine helps stamp that experience into memory, not as a sentence, not as a thought, more like a quiet map. This tasted good. This gave energy. This is worth finding again. That reward system once helped humans survive in a world where energy-rich food was not always easy to find. A honeycomb in the wild was rare. A ripe fruit tree was seasonal. A fatty piece of meat required effort, tools, skill, and luck. Today, many foods combine several rewarding signals at once. Fat and sugar. Fat and salt. Starch and salt. Creaminess and sweetness. Crunch and flavor. Soft texture and quick swallowing. A cookie, a milkshake, a pizza slice, a pastry, a bowl of chips, or a sweet cereal can send many pleasure signals together. These foods can be easy to eat quickly because they require less chewing, less effort, and often create less fullness bite for bite than slower foods like beans, oats, vegetables, or whole fruit. This does not mean one food is morally good and another is morally bad. Food is food, but different foods speak to the brain in different ways. A whole apple contains water, fiber, sweetness, scent, and crunch. It takes time to chew. It fills space in the stomach. Its fiber slows digestion. A sweet drink may contain energy too, but it can pass through the mouth in seconds with little chewing and less stretch in the stomach. The body receives the fuel, but the fullness signal may not rise in the same way. Texture matters. Foods that melt quickly in the mouth can be eaten faster. Soft bread, cream-filled desserts, cheese sauces, and sweet drinks may disappear before the gut has had much time to send fullness messages upward. Fullness hormones from the intestine do not arrive instantly. The stomach needs time to stretch. The gut needs time to sense nutrients. The brain needs time to receive the report. When eating happens quickly, energy can enter before the body fully notices. Memory matters too. The smell of popcorn can bring back a movie theater. A certain candy can bring back childhood. A warm drink can feel linked to comfort. A salty snack can become tied to a couch, a screen, and the end of a long day. The brain does not store food only as fuel. It stores food as place, mood, sound, smell, texture, and routine. This is why hunger and craving are not the same. Hunger asks for energy. Craving often asks for a specific experience, a taste, a feeling, a familiar reward, a small moment of relief. Highly rewarding food can meet both at once. It can answer the body's energy need while also touching memory, habit, and pleasure. And when these foods are nearby, cheap, visible, and easy to reach, the body may receive more energy than it consciously tracks. A handful from a bag, a few bites while cooking, a sweet drink beside a desk, a snack during a late-night show. Each moment may feel small, but the body records energy, even when attention is somewhere else. This is not weakness. It is an ancient reward system meeting a world designed around access, flavor, speed, and memory. The brain is doing what it has always done. It is noticing what feels valuable. It is remembering what brought comfort. It is guiding the body toward easy energy. And when reward, hunger, habit, and availability line up, storage can happen almost quietly, before the person feels they have done anything unusual at all. When reward, hunger, habit, and easy access overlap, the body may take in more energy than it fully notices. Stress can make that overlap stronger. Stress is not only a feeling, it is a body state. It changes heart rate. It changes breathing. It changes digestion. It changes blood sugar. It changes sleep. It changes what kinds of food feel most comforting or easy to reach. The stress response begins in the brain, but it quickly spreads through the body. When the brain senses challenge, it can activate the sympathetic nervous system. This is the part of the nervous system that helps the body respond quickly. It can raise heart rate, sharpen attention, and send more blood toward muscles. One of the main chemicals involved is adrenaline. Adrenaline is released by the adrenal glands, two small glands that sit on top of the kidneys. In a sudden, stressful moment, adrenaline helps the body act. The heart beats faster. The airways open a little wider. Stored fuel becomes easier to use. This is useful if danger is brief. A loud sound, a near fall, a fast reaction while driving, a sudden problem that needs attention. But the body also has a slower stress system. This system involves a hormone called cortisol. Cortisol is also released by the adrenal glands. It helps manage energy during longer challenges. It can raise blood glucose by encouraging the liver to release more fuel. It can affect appetite. It can change inflammation. It can influence where the body stores fat over time. Cortisol is not bad. The body needs it. In a healthy daily rhythm, cortisol is usually higher in the morning, helping the body wake, and lower at night, helping the body settle. It follows a quiet 24-hour pattern tied to sleep, light, and the body's internal clock. But when stress lasts for days, weeks, or months, that rhythm can become disturbed. The body may stay more alert when it should be winding down. Sleep may become lighter. Hunger may become stronger or less predictable. Digestion may feel unsettled. Cravings may shift toward foods that are quick, rich, sweet, salty, or familiar. This makes sense from a survival point of view. If the body believes it is under pressure, easy energy can feel important. A stressed body may not ask for a slow meal with careful preparation. It may ask for fast fuel. Something soft, something sweet, something salty, something that feels known. Stress can also affect blood sugar patterns. When cortisol is higher, the liver may release more glucose into the blood. This gives the body fuel for action. But if the person is sitting still, working at a desk, lying awake, or dealing with worry rather than physical danger, that extra fuel may not be used in the same way. The pancreas may release more insulin to help move glucose out of the blood. Over time, repeated stress, short sleep, and irregular meals can make the body's fuel handling less smooth. Stress can change storage indirectly too. A person under pressure may have less energy for planning. Cooking may feel harder. A regular walk may disappear. Bedtime may drift later. Groceries may become whatever is easiest. Meals may become faster. The body may move less, not because it is lazy, but because attention and energy are being spent on getting through the day. Long-term stress can narrow the world. The nervous system becomes busy watching for problems. The brain gives priority to what feels urgent. Emails, bills, deadlines, noise, conflict, a sick family member, a long commute, a schedule that never feels finished. In that state, gentle routines can quietly fall away. And when routines change, the storage system feels it. Less sleep can raise hunger. Less movement can leave more fuel unused. More quick food can bring more energy before fullness catches up. More cortisol can shift blood sugar and appetite. More stress can make the body hold tension, water, and habit all at once. Stress does not create weight gain by one direct path. It creates conditions. A body that is more tired. A brain that is more alert. A gut that is less settled. A routine that is less steady. A storage system receiving stronger signals to prepare, protect, and hold on. And among all the ways stress enters the body, one of the quietest is also one of the most powerful. It reaches into the night, changes the depth of rest, and reshapes the chemistry of hunger before morning arrives. As stress reaches into the night, sleep becomes part of the storage story. Sleep may look passive from the outside. The room is dark. The body is still. Breathing slows. The eyes close. But inside, sleep is active. Hormones rise and fall. Body temperature shifts. The brain changes its electrical rhythm. The liver manages fuel. Muscles repair small daily damage. The immune system adjusts its signals. And the body prepares for the next day of hunger, movement, and energy use. When sleep is shortened, that preparation can change. Even one rough night can make hunger feel different the next day. One reason involves ghrelin. Ghrelin is the hormone made mostly in the stomach that tends to rise before meals. It helps signal hunger to the brain. When sleep is too short, ghrelin may rise, making the body feel more interested in food. Another signal is leptin. Leptin is made by fat cells and helps tell the brain about stored energy. When sleep is disrupted, leptin signaling can shift too. The body may receive a softer fullness message and a louder hunger message at the same time. This does not mean a person has failed. It means the chemistry of appetite has changed before the day has fully begun. A tired body often asks for quicker energy. After a short night, the brain may respond more strongly to foods that are sweet, salty, fatty, or easy to eat. A pastry in a glass case, a sweet drink beside a desk, a bag of chips during a late afternoon slump, a warm, rich meal at the end of a long day. These foods may feel more appealing when the body is tired, partly because sleep loss can increase activity in reward pathways. Reward pathways help the brain notice what feels useful, pleasant, or worth repeating. When sleep is short, the brain's control systems may be less steady, while reward signals become more noticeable. The result can be simple and familiar. Food feels more tempting. Waiting feels harder. Energy-rich choices feel more comforting. Sleep also affects how the body handles glucose. Glucose is the simple sugar that enters the blood after carbohydrates are digested. After a meal, insulin helps move glucose from the blood into cells. But sleep loss can reduce insulin sensitivity. Insulin sensitivity means how well cells respond to insulin's message. When cells are more sensitive, glucose can move into them more smoothly. When cells are less sensitive, the body may need more insulin to handle the same amount of glucose. This means the same meal can be received differently after good sleep, compared with poor sleep. A bowl of oatmeal, a plate of rice and vegetables, a sandwich, a piece of fruit. The food may be the same, but the body's internal state is not. After deeper sleep, the system may manage incoming fuel with more ease. After short or broken sleep, blood sugar and insulin patterns may become less smooth. This is one reason sleep belongs in the science of weight gain. It does not add energy by itself, but it changes hunger, reward, hormones, and fuel handling. Sleep timing matters too. The body follows a daily rhythm, often called the circadian rhythm. Circadian means about a day. This rhythm is guided by light, darkness, meals, movement, and routine. At night, the body is usually preparing for rest. Body temperature begins to drop. Melatonin rises in darkness. Digestion tends to slow. The brain shifts towards sleep. But when bedtime moves later or sleep is broken by light, noise, stress, screens, or irregular schedules, the rhythm can blur. A tired person may stay awake longer. More waking hours can mean more chances to eat. Late-night food may arrive when the body is less prepared to manage it. The stomach can still digest. The pancreas can still release insulin. The liver can still sort fuel. But the whole system is working in a different state. Sleep is not separate from metabolism. It is part of the way metabolism is organized. It helps set the tone for hunger. It helps shape fullness. It helps the body decide how smoothly glucose moves from blood into cells. It helps the brain respond to reward with a steadier hand. So when sleep becomes short, irregular, or shallow, weight gain can become easier through many quiet paths at once. More hunger, stronger cravings, more late eating, less movement from fatigue, less smooth blood sugar control. A tired body does not meet food as the same body it was after rest. it receives the same meal through different chemistry. And that chemistry changes not only across one night, but across the deeper rhythm of day and darkness that guides the body hour by hour. The chemistry of a tired body does not appear at random. It follows the deeper timing system that runs through nearly every cell. This timing system is called the circadian rhythm. Circadian means about a day. It comes from Latin words meaning around and day, and it describes the roughly 24-hour cycle that helps organize sleep, hunger, temperature, digestion, alertness, hormones, and energy use. The body does not experience every hour the same way. Morning is not midnight. Afternoon is not deep night. A meal eaten after waking does not meet the exact same body as a meal eaten near bedtime. One of the main timekeepers sits in the brain. It is called the suprachiasmatic nucleus. The name is long, but its location is simple. It sits above the place where the optic nerves cross. Because it receives information about light from the eyes, it helps the body know when the outside world is bright or dark. Morning light tells this clock that the day has begun. Darkness helps allow melatonin to rise. Melatonin is a hormone that helps signal biological night. It does not knock the body unconscious. It simply tells the body that darkness has arrived and rest should become easier. Other clocks exist throughout the body too. The liver has timing patterns. The pancreas has timing patterns. The gut has timing patterns. Muscle and fat tissue have timing patterns. These smaller clocks help organs prepare for different jobs at different times. During the active part of the day, the body is usually more ready to receive food. The stomach and intestines are more awake. The pancreas is prepared to release insulin. Muscles may be more ready to use glucose, especially if the body is moving. Body temperature is higher during much of the daytime, and many enzymes work smoothly in that active rhythm. Food arriving during this window meets a body that is expecting fuel. At biological night, the signal pattern changes. The body begins preparing for repair and rest. Core temperature tends to fall. Melatonin rises in darkness. Alertness decreases. Digestion can slow. Insulin response may become less efficient at night, meaning the body may not move glucose out of the blood as smoothly as it does earlier in the day. This does not mean food at night becomes magically different. A gram of carbohydrate is still a gram of carbohydrate. A gram of fat is still a gram of fat. But the body receiving that food is in a different state. The lights are dim inside the system. The organs are following a quieter rhythm. The same meal can land differently when the body expected sleep instead of digestion. This is why late eating, irregular sleep, and changing schedules can blur the body's timing. A person who stays up late may feel hungry simply because they are awake for more hours. A person who works overnight may eat when their internal clock is calling for rest. A person who sleeps at different times on weekdays and weekends may give the body mixed signals about when day begins. Shift work is one of the clearest examples. Nurses, factory workers, drivers, emergency workers, hotel staff, security workers, and many others may work through the night, while the body's ancient clock still responds to light and dark. Even if someone adapts to the schedule, the body may still receive conflicting messages. Bright light at night, sleep during the day, meals at unusual hours, caffeine late in the shift, less sunlight after waking, less regular digestion. These mixed signals can affect hunger, blood sugar control, and energy use. Routine matters because the body prepares. If breakfast usually happens at 8, lunch at noon, dinner at 6, and sleep at 11, the body can begin to predict the rhythm. Hormones, stomach movement, alertness, and temperature can align around the pattern. But when timing changes often, the body has less rhythm to follow. A late dinner one night, a skipped breakfast the next, a midnight snack after a long screen session, a weekend sleep schedule shifted by several hours. Each change may be small, but together they can make the internal clocks less coordinated. The body still does its best. The stomach still digests. The liver still sorts fuel. The pancreas still releases insulin. The muscles still store glycogen. Fat tissue still listens and responds, but the timing may be less smooth. Weight gain, then, is not only about what enters the body, it is also about when it enters and what state the body is in when it arrives. Rested or tired, active or still, daylit or dark, calm or stressed, early in the rhythm or deep in biological night. The body is always reading time, even when no clock is nearby. And as time shapes hunger, digestion, insulin, temperature, and storage, another quiet force keeps influencing where fuel goes. The pattern of movement across the day. The pattern of movement across the day changes what the body does with fuel. Movement is often described in one narrow way, as burning calories. But inside the body, movement is more than fuel being spent. It is a signal. When muscles contract, they ask for energy. A muscle fiber squeezing during a walk, a stretch, a climb, or a reach can pull glucose from the blood and use it to make movement happen. Glucose is not only moved into muscle by insulin. Working muscle has another pathway. During movement, muscle cells can bring more glucose transporters to their surface, helping glucose enter even when insulin is not doing all the work by itself. A transporter is like a small doorway in the cell membrane. When more doorways open, glucose can move from the blood into the muscle more easily. This is one reason a walk after a meal can change how the body handles blood sugar. The muscles are not just spending energy, they are receiving it. They are clearing some of it from the blood. They are turning food chemistry into motion. Muscle also stores glucose as glycogen. After a person moves, especially after using larger muscles in the legs, hips, back, or arms, some glycogen may be used up. Later, when food arrives, those muscles may be ready to refill part of that stored fuel. This makes muscle a kind of storage space, not the same as fat tissue, not long-term storage for months, but a short-term fuel tank that can be filled, emptied, and filled again. The thigh muscles alone are large. The glute muscles in the hips are among the biggest muscles in the human body. The back, calves, chest, and shoulders all add more tissue that can use and store fuel. A body with more active muscle has more places for glucose to go. Movement also affects circulation. When muscles contract, They help push blood through veins back toward the heart. This is especially clear in the legs. The calf muscles sometimes act like a small pump, squeezing veins during walking and helping blood move upward against gravity. This movement of blood helps deliver oxygen and fuel, and helps carry away waste products made by working cells. Even gentle movement changes the body's internal traffic. Standing, walking to another room, folding clothes, carrying groceries, cleaning a counter, climbing a few stairs, pacing during a phone call. These small actions may not feel like exercise, but they still count to the body. Scientists sometimes call this non-exercise activity. It means the energy used outside planned workouts. The full term is non-exercise activity thermogenesis. But the idea is simple. It is the energy used by ordinary movement. One person may sit almost completely still for hours. Another may stand often, shift position, walk around the house, gesture while talking, cook, tidy, stretch, or take short walks without thinking much about it. Across 1 hour, the difference may seem small. Across a whole day, it can be much larger. Across months or years, the pattern can help shape how much energy is used and how often muscles are asked to receive fuel. This does not mean everybody needs constant motion. The body also needs rest. Stillness is part of repair. Sleep is part of regulation. Sitting can be part of work, safety, comfort, and recovery. But long stretches of stillness change the fuel conversation. If muscles are not contracting often, they are not asking for as much glucose. They are not emptying glycogen as much. They are not sending the same signals for fuel uptake. The body may still receive energy from meals, but fewer muscles are calling for it in the moment. Then more of that energy has to be handled by other systems. Some may be stored as glycogen. Some may be used by organs. Some may be saved as fat if more energy keeps arriving than the body uses over time. Movement also affects appetite and sleep in indirect ways. A body that moves gently during the day may sleep more deeply at night. Better sleep can help hunger signals feel steadier. Movement can also reduce stress for many people, which may soften the signals that pull the body toward quick energy and late-night eating. So movement shapes storage through many quiet paths. It uses fuel. It opens glucose doorways in muscle. It refills glycogen tanks. It improves blood flow. It helps daily rhythms. It can steady sleep and stress. It gives incoming energy somewhere useful to go. The storage system is shaped not only by meals, but by the soft pattern of motion or stillness across the whole day. And because those patterns repeat, the effects may gather slowly, almost invisibly, until small daily differences become part of the body's longer story. Because movement, sleep, stress, timing, hunger, and storage repeat day after day, weight gain often happens slowly, not as one clear moment, not as one meal that changes everything, but as a long pattern of small differences. Energy comes in through food and drink. Energy goes out through resting metabolism, digestion, movement, heat production, tissue repair, and daily activity. When those two sides are close, body weight may stay fairly steady. When a little more energy comes in than the body uses again and again, the body may begin saving the difference. At first, the change can be too small to notice. A few extra bites, a sweet drink, a shorter walk, a week of poor sleep, a stressful month, a winter with less daylight and less movement, a new job that replaces walking with sitting, a medication that increases appetite, a hormone shift that changes water and hunger. None of these has to feel dramatic, but the body records repeated patterns quietly. A small difference each day can become more meaningful over time. This is the slow mathematics of biology. Even a little extra stored energy, repeated across weeks and months, can gradually become visible. Not because the body changed suddenly, but because the same direction kept repeating. The body is always balancing the moment against the long term. Today's meal, tonight's sleep, this week's movement, this month's stress, this season's routine. All of it leaves small traces. Some traces disappear quickly. Water changes. Digestion moves. Glycogen fills and empties. Salt rises and falls. But some traces can last longer when the pattern continues. Fat cells may store more triglyceride. Muscles may lose or gain glycogen. The gut may carry more or less food at different times. The body may hold fluid during heat, soreness, stress, or hormone shifts. This is why the scale can be both useful and misleading. It gives one number, but that number is made of many things at once. Fat tissue is part of it. Water is part of it. Glycogen is part of it. Muscle is part of it. Bone is part of it. Blood volume is part of it. Food moving through the stomach and intestines is part of it. Inflammation and repair can be part of it. A salty dinner can be part of it. A hard workout can be part of it. A poor night of sleep can be part of it. A warm day with more sweating can be part of it. The scale cannot separate these layers. It cannot say, this pound is water. This pound is stored carbohydrate. This change is digestion. This change is tissue repair. This change is long-term storage. It can only show the total weight of the body at one moment in time. That is why body weight can rise and fall from day to day, even when long-term fat storage has barely changed. A person may weigh more after eating a large meal, simply because the food and fluid are still inside the body. They may weigh more after eating more sodium, because the body holds water to keep blood chemistry steady. They may weigh more after a hard workout, because sore muscles can hold fluid as they repair tiny damage. They may weigh less after sweating, using glycogen, or having less food in the digestive tract. These short changes can sit on top of slower changes, like ripples moving over deeper water. Long-term weight gain is usually the deeper current. It comes from repeated energy storage over time. The body does not need to store much on any single day for the pattern to matter. A small surplus can hide beneath ordinary life. It can be softened by water shifts, masked by digestion, or made invisible by daily variation. Then, after months, the trend becomes easier to see. This is why weight gain can feel surprising. The body may have been changing in tiny increments while attention was elsewhere. Working, resting, recovering, eating familiar meals, sleeping less, moving less, handling stress, following the same evening routine. The body does not announce every small storage decision. It simply keeps adapting. It uses what it needs. It stores what remains. It holds water when chemistry asks for water. It repairs tissue when tissue needs repair. It fills glycogen when muscles and liver have room. It stores fat when extra energy keeps arriving beyond immediate use. By now, the number on the scale no longer looks like one simple answer. It looks more like a shadow cast by many systems at once. A shadow of blood, water, fuel, tissue, hormones, digestion, movement, sleep, stress, and time. And beneath that shadow, the body is still doing what it has done all along. Trying to stay steady, trying to stay prepared, trying to hold on to what it may need later. By the end of this quiet journey, weight no longer looks like one simple thing. It looks like a living record of many systems working together. Food becomes molecules. Carbohydrates become glucose. Fats become fatty acids. Proteins become amino acids. The blood carries those pieces through the body, past the liver, the muscles, the brain, the gut, and the soft storage tissue beneath the skin. Some fuel is used right away. The heart keeps beating. The lungs keep moving. The kidneys keep filtering. The brain keeps listening to the body. Cells keep repairing tiny damage from ordinary life. Before storage begins, the body is already spending energy just to stay alive. Then the body saves what it can. Glucose can be stored as glycogen in the liver and muscles. Glycogen is short-term stored carbohydrate. It helps the liver keep blood sugar steady between meals. It helps muscles move through walking, lifting, climbing, and standing. And because glycogen holds water with it, the body can become heavier without much fat changing at all. Water follows salt. Water follows stored carbohydrate. Water gathers around healing tissue. Water moves through the blood, cells, gut, and spaces between tissues. This is why the scale can shift quickly. It is not measuring one substance. It is measuring the whole body in one passing moment. Longer-term storage happens in fat cells. Those cells store energy as triglycerides, compact molecules made from fatty acids and glycerol. Fat is efficient because it holds more than twice as much energy per gram as carbohydrate or protein. That made it useful across human history when food was not always nearby, predictable, or easy to find. Stored energy could help a person survive cold, illness, travel, hunger, pregnancy, and long gaps between meals. The body does not store fat because it is broken. It stores fat because storing energy helped life continue. But fat cells are not silent. They grow, they shrink. They receive blood. They respond to insulin. They release hormones. They send leptin to help tell the brain about stored energy. They release adiponectin, which helps shape how the body handles sugar and fat. Adipose tissue is not just padding. It is living communication. The brain listens to these signals. Deep inside the brain, the hypothalamus helps regulate hunger, thirst, temperature, sleep rhythms, hormone release, and energy balance. It compares incoming fuel with stored fuel. It compares today's signals with familiar patterns. It notices sleep, stress, timing, hunger, fullness, and routine. The body often protects what has become familiar, because stability has always been safer than chaos. This is why weight gain can become persistent. It is not one moment. It is a pattern the body may slowly learn. A regular mealtime, a late bedtime, a stressful season, a shorter walk, a familiar snack, a shift in hormones, a medication, a tired morning, a modern world full of easy food, bright light, long sitting, and constant pressure. Each piece may be small, but the body does not live in isolated pieces. It lives in repeating signals. Sleep changes hunger. Stress changes appetite and blood sugar. Movement changes how muscles receive glucose. Circadian rhythms change how the body handles food across day and night. Highly rewarding foods can speak strongly to reward pathways built for survival. The same storage system that once protected people from scarcity now lives in a world of constant availability. So the body may hold on. It may hold water. It may refill glycogen. It may store extra energy in fat cells. It may defend a pattern it has come to know. And none of this turns weight gain into a moral story. It is biology. It is storage. It is signaling. It is protection. It is repetition over time. A body gaining weight is not simply changing on the outside. It is adapting on the inside. Sorting fuel, reading hormones, watching sleep, responding to stress, listening to hunger, holding energy for a future it cannot fully predict. And maybe that is the calmest way to understand it. The body is always trying to keep itself alive, stable, and prepared. Even when the modern world gives it more to store than it once expected. Even when its old survival systems meet a new kind of abundance. Even when the number on the scale seems simple, the story beneath it is wide, patient, and deeply human.